So, when you think about Mars a billion years ago, what pops in your head? Probably the same thing we see today, right? A cold, red, dusty desert. But what if I told you that's the end of the story, not the beginning? The real story of Mars's past is so much more dramatic. It's a tale of a lost world, a world that might have been an even better place for life to start than our own planet.
Just look at this. It's night and day. On the left, yeah, that's the Mars we all know. But on the right, that's Mars from 4 billion years ago. We're talking a world with a thick atmosphere, comfortable temperatures, and huge oceans of liquid water. It wasn't the red planet back then, it was a blue planet. So the big question is, how in the world did it go from a potential paradise to a frozen wasteland?
Okay, let's rewind all the way to the beginning, to Mars's watery youth. Billions of years ago, you could make a pretty strong case that Mars was a better bet for starting life than even early Earth. Seriously, it had all the right ingredients, and it had them way earlier.
To really get a grip on this story, we need a roadmap. This timeline here breaks down the major chapters in Martian history. You've got the planet's formation, then you get into the Noachian, that's the good stuff, the wet era. After that comes the Hesperian, this big transition period, and finally, the long, cold Amazonian desert age, which is where it's still at today.
So during that early Noachian period, Mars was just a perfect incubator for life. You had volcanoes erupting everywhere, which built up a thick, warm atmosphere. And that atmosphere meant you could have clouds, rain, rivers carving out valleys, and giant lakes. And the rain? Well, it was probably acidic, but that was actually a good thing. It would dissolve rocks, releasing all these minerals and nutrients into the water, creating what you could call a chemical buffet for any tiny microbes just trying to get started.
So Mars had it all going on. It was on the right track. But then, around 4 billion years ago, something absolutely catastrophic happened. The planet's protective shield just failed, and that one single event sealed its fate forever.
That shield is called a magnetosphere. The best way to think of it is as a planet's invisible force field. It's generated by the churning of a hot, molten core, like a dynamo, and its whole job is to deflect this constant, dangerous stream of particles flying off the sun, which we call the solar wind. Earth has a nice, strong one, and early Mars did too, until its core cooled down and the dynamo just shut off.
So what happens when that shield goes down? Well, that solar wind is no longer being blocked. It just slams directly into the upper atmosphere. These charged particles come flying in and literally knock the air molecules one by one right out into space. You do that for millions of years and the atmosphere gets completely blown away.
And the consequences were just devastating. The dominoes fell one after another. No shield meant no air. No air meant the water either boiled off into space or froze solid. And without air and water on the surface, the chances for life just plummeted to zero.
Now, for billions of years, it really seemed like that was the end of the story, a dead planet. But just recently, a modern-day explorer, NASA's Perseverance rover, found this incredibly tantalizing clue from that ancient, watery past, a little fossil from the past.
And Perseverance wasn't just wandering around, hoping to get lucky. It was sent to a very specific place called the Jezero Crater. Scientists know this crater used to be a giant lake, and a river flowed into it, forming a big delta. And on Earth, river deltas are amazing at trapping and preserving signs of life in their rock layers. It's all about location, location, location.
Okay, now we have to be super precise here. As Dr. Ed Clutis, one of the mission scientists, points out, this isn't proof of life. That's not what we're saying. What Perseverance found are called biosignatures, potential remains of life that just hint that something incredible might have happened there.
So what are these clues exactly? Well, first, organic molecules, the basic building blocks of life. But the really striking find are these things they're calling leopard spots, these little clusters of iron-rich minerals. And here's the kicker. On Earth, when we find this exact combination of minerals and organics together, it's almost always connected to biology. But here's the catch. The rover's instruments on Mars can only tell us so much. To know for sure if these spots are actually fossilized microbes, we have to get those rock samples back here to our advanced labs on Earth. And that, my friends, is a massive undertaking. The earliest we might see them is 2031. So we've got a while to wait. All right, so let's fast forward from that super promising ancient era, past the Great Decline, and land right on our main question. What was Mars like 1 billion years ago? Well, the vibrant, watery youth was long, long gone. This was the era of the Big Freeze.
The very first thing you'd notice is the cold. I mean, the average temperature on the surface had crashed to a staggering minus 60 degrees Celsius. That's minus 76 Fahrenheit. We're talking about a deep, relentless freeze that had completely taken over the planet.
And you can really see the dramatic change in this chart. At 3.5 billion years ago, things were already going downhill. The atmosphere was shrinking, the water was disappearing. But by 1 billion years ago, the atmosphere was paper thin, less than 1% of Earth's, and there was just no stable liquid water left on the surface at all. It was gone.
But the planet wasn't completely dead yet. While most of the smaller volcanoes had gone silent, the biggest volcano in the entire solar system, Olympus Mons, was still kicking. Its gigantic eruptions would have spewed greenhouse gases into the thin air, warming the planet up for a little while and melting some of the subsurface ice, which would trigger these huge flash floods. You can almost think of these eruptions as the planet's last desperate attempts to stay habitable.
So what does this all mean? Well, if any of those ancient Martian microbes managed to survive, the surface was definitely not an option anymore. Their only chance, their last refuge, would have been to retreat deep underground, clustering around hydrothermal hotspots where there was still some warmth and, maybe some water, shielded from all the radiation and the brutal cold up above.
The story of Mars really seems like one of tragic loss, doesn't it? But there's one last kind of mind-bending chapter to think about, a theory that connects the death of Mars directly to the beginning of life, right here on Earth.
How is that even possible? Well, it's because the planets have been trading rocks for billions of years. We have found over 400 confirmed pieces of Mars that have landed right here on Earth as meteorites. They were blasted off the Martian surface by an asteroid impact and eventually made the journey to our world.
This all leads to a really cool idea called the panspermia theory. It's the theory that life doesn't necessarily have to start from scratch on every single planet. Instead, it could be seeded, traveling from one world to another, tucked away safely inside rocks, just like those Martian meteorites, surviving the harsh journey through space.
And this is what makes the theory so compelling when you think about it. Remember, early Mars was a paradise for microbes, while early Earth was still kind of getting its act together. Life had a significant head start on Mars. So it's totally plausible that microbes popped up there first, and then one of those big asteroid impacts blasted a piece of Martian rock with life on it toward a young, waiting Earth. Which leaves us with this one last, pretty wild thought. If the first spark of life in our cosmic neighborhood didn't happen here, but on that vibrant blue Mars, and a piece of that life hitched a ride on a rock and made the journey to our planet, then doesn't that mean, in a way, that we're all the descendants of Martians? Searching for life on Mars might actually be searching for the oldest branches of our own family tree.